Hello everyone, welcome to Engineering Chalkboard. Today I'm going to take you through a next question which is about an overhanging beam. So I'm going to take you through and we're going to read the question together so that we may be able to know what our question is asking us to solve. Figure 1 shows an overhanging beam. This is our figure 1 here. I hope you can see it. Shows an overhanging beam. So A says plot the influence line diagram for reaction at A, reaction at B, and 3, shear force at point E. And B, determine the maximum negative shear force and maximum bending moment at point E. Here, when a uniformly distributed load of 30 kN per meter and 6 meter long crosses the beam from C to D, which is 8 marks. And our question A takes 12 marks. So we are going to start with our A, and we are going to draw using this beam, which is an overhanging beam supported 20 meters span of the supports and 2 meters hanging and the 4 meters hanging on the other side. And our UDL is of 6 meter long and 30 kilonewton meter per meter, which is our moving load. So our load will be moving in our girder or beam. But in our question A, we just only wanted to draw the reactions at point A and at point B. And then we draw the shear force, the ILD, the influence line diagram of the shear force at point E. So that is what the examiner is telling us to do in our first question. So let me take you through. So in this page, as you can see, we have the same girder here, and so what will be required to is we're going to extend the lines down. I hope everything is clear up to where you want to reach it. So up to there, even this other point, just a sketch, should not be accurate, just for analysis. And this one, but just make sure that your drawing is neat like mine. And for point D, it's somewhere there. So we're going to first draw our reaction at point A. Our reaction A. So you should draw something like this. This is what the examiner is telling you to draw and to come with. Obviously at the supports, it is always taken, the reaction is always taken as 1, and at B it is always 0. So it should be 1 here. So let's say it is somewhere there and extend it down. So your line should touch 0 and 1 here. So you must indicate 1 and draw there and draw a line here. Okay, so now we have to calculate the ordinates at point C. Okay, at point A we have it, and now and at our point D. So our ordinates for reaction A is going to be ordinate at C. So it is our whole span is going to be L, which equals to 20, and from C to A we are going to name it A, which equals to 2 meters, and from B to D we are going to name it B. So here it is going to be B, and here at A. So to calculate our ordinate at C, the formula is always L plus A all over L. So it equals to 20, our whole span, plus A, which is 2 all over 20, which equals to 22 all over 20. Into decimal form, it is going to be 1.1. So you have to indicate here that it is 1.1. Okay, and at our reaction at our ordinate at point D, it is always B. It is B all over 20. So it is 4 all over 20, which is equals to 0.2. Here it is 0.2. So this is negative and this is positive. So our reaction at B say there, and so at B here we're going to take it as 1, and so, and at our reaction at point at support A, it is going to be 0. It's 0, so it must be fast. I hope that you are understanding. So our influence line for reaction at B, at A, support A equals to 0. So our shear force at E, we're going to drop our point E somewhere here. Like this, and so we're drawing like this. You should draw, and also for this one. Yes. Our ordinate at C. So this one is RA, ILD for RA. This one is for ILD for RB. ILD for shear force at E. So our ILD influence line diagram for shear force at E. So ordinate at C, it is 2 all over L, A all over L, 2 all over 20, which is equals to 0.1, and for at D, it is 4. Just take the distance, so it is B all over L, 4 all over 20, it is 2, 10, by 2, 1 by 2, 5, this is 0.2, and for our shear force at for our ordinate at E, it is the distance from here to here all over the whole span. So for this triangle, it is 8 minus 20, which is 12 all over 20, which when you divide equals to 0.6, and this one is 8 all over 20. When you divide it is 0.4. So this is what you should do. So here it is 0.2. So this is our influenced line diagram for our shear force at E. This is positive. This is positive. This is negative. This is negative. And when we jump to the next our question, it says that you should determine the maximum negative shear force and maximum bending moment at point E when a uniformly distributed load of 30 kilonewton per meter and 6 meter long crosses the beam from C to D. So in this question, for you to find the maximum negative shear force, we are going to place the loads, our UDL, which is the 30, which is this one, 30 kilonewton per meter. We're going to place them where our shear force is, our maximum shear force is negative. So we're going to place them at these points. So there, there. This is 30 kilonewton per meter, 30 kilonewton per meter. For you to calculate the shear force, so we're going to multiply the load by the ordinate so that we're able to find the maximum negative shear force in this triangle. And so I'm sorry, for you to calculate the maximum negative shear force, we are going to multiply the area of this triangle by this intensity load of 30 kilonewton per meter plus this other triangle here. So we already have the formula, which is a half multiplied by the base, which is 8 from E to A, multiplied by the height, which is 0.4, multiplied by 30. Plus a half multiplied by the base, which is 4, multiplied by the height, which is 0.2, multiplied by 30. So when you do, and when you sum up this whole equation, our answer is going to be 60 kilonewtons. This is our maximum negative shear force for this diagram. For our maximum bending moment, we are going to redraw again so that we're able to calculate afresh, to calculate and find our maximum bending moment. And for us to calculate this load, our UDL must be placed subdividedly equally to point E, because at our question, for our question, we have to determine the maximum negative shear force and bending moment at point E. So we must place our load of 30 kilonewton equally to point E. So this is what I'm saying. For our maximum bending moment at this section E, it takes the section X, this section, because we have placed the UDL at the span at point E. Because our UDL is it is not longer than the span, therefore we must determine this point X so that we're able to know how our UDL has divided our support from A to B. And so for maximum bending moment at section, it takes the section X divides the load in the same ratio as it divides the beam. We must have to find X and find the other so that we're able to know how 6 it is being divided into our whole beam. See, this is what I'm saying. So it is X. Okay, it is, let me write here, X all over 6, no, all over 8, the distance from A to E, all over 8, let me write again, X all over 8 equals to 6 from the whole length of our load all over 20, the whole span. So we find X equals to 48 all over 20, which is equal to 2.4. Therefore, when we minus 2.4, this other, it will be 3.6, sorry. Here to here it is 2.4 and 3.6. And we should draw our influence line diagram for this. As fast as you can. Then this is our span. Now point E, somewhere there. So our bending moment will be a triangle from there. There. from this point that point. So the examiner is actually telling us to find the area of this triangle. This triangle. This triangle here. So this is positive, positive, this is negative, negative. So how the UDL will be acting to our influence line diagram as it moves at point E. And this is the maximum bending moment that we are told to calculate. So our ordinates at point C it is going to be A into L minus Z into L. A equals to 2, B equals to 4, and L equals to 20, whereas Z equals to 8 meters. All these are in meters. So our point A, it is 2 into 20 minus 8 all over 20. And when you calculate all of that, we are going to find 1.2. So our point, so for our point E, at E, it is A, it is Z into L minus Z all over L. 8 into 20 minus Z, which is 8 all over 20. When you do all of this, you should get 4.8. And at D, this is how you should arrange your work. It is B Z all over L. So our B, we have it is 4 multiplied by Z, which is 8 all over 20. So this is 32 all over 20. And you should, when you key into your calculator, it is 1.6. So it is 1.6, 4.8, and 1.2. This is what you should get. And to calculate our maximum bending moment, hope that everything is clear. Maximum bending moment equals to the area, the sum of area of these two triangles multiplied by their load intensity, which is 30 kilonewton per meter, which is half into, half multiplied by base, multiplied by, this is the trapezium, it's a trapezoidal, into A plus B, which are the sum of these two parallel lines. So these two parallel lines, meaning that we should have calculated our point there and our ordinate at this point. So for us to calculate the ordinate at this point, it is x, this is, take that as x, We remember our previous formula. It is x all over 4.8, which is equal to 8 minus 2.4 5.6 all over 20 all over 8, sorry. So our x, we should get 3.36, and so let's take this one as y. So it is y equals to y all over 4.8 equals to from this point to this point it is 12. So 12 minus 3.6 8.4, so it is 8.4 all over 12, and our y, you should get it as, when you key in this into a calculator, it is 3.36. So this is 3.36. So coming back into calculating our maximum bending moment, it is 4.8 plus 3.36 multiplied by height, which is from this point to this, it is 2.4, multiplied by all this, multiplied by 30, and you close in, plus a half multiplied by 4.8 plus 3.36 multiplied by the height, which is 3.6, multiplied by 30. And when you key all this into your calculator, I'm sorry because camera is not focusing that lot, you should get the maximum bending moment as 734.4 kilonewton meters, and this is our maximum bending moment. I hope you all enjoyed the lesson and this example. Thank you.